This is a very interesting question, pretty difficult. We need to really look at what's happening here because now there are two beams in this question. But we do note that everything is in equilibrium, everything is not moving. So the answer to this question is B. And let's just look at option B first. Option B, we see that the small beam is balanced. The shorter one, the 40 cm one, is balanced. It's not moving. It's at equilibrium. This must mean that the moment caused by Y and the moment caused by Z, they are the same. They balance each other. So one is a clockwise moment, one is an anti-clockwise moment. So that's what I did for option B. The weight of Y multiplied by the distance of Y should be equals to the weights of Z multiplied by the distance of Z. And since the distance of Y away from the pivot and the distance of Z away from the pivot is the same at 20 centimeters, the only way for the smaller beam to balance itself is that the two objects have the same mass and the same weights. Okay, so therefore that's how you can get the answer of B, where object Y and Z has the same mass or the same weights. Now, we look into option A now and see why is that wrong. And we see that the long bar, the 1 meter bar at the top, is balanced. So again, using principle of moments, the moment caused by X must balance the moment caused by everything on the right hand side. So the moment caused by X is WX times dx, and this must balance, this anti-clockwise moment must balance all the clockwise moment. So what is the clockwise moment? Basically, if you look at the right side of the long bar over here at my laser pointer, at this point you have a combined weight of Y and Z. So Y and Z here, combined weight pulling down at this point, and this combined weight of Y and Z is at the distance of 30 cm away from the pivot. So that's exactly what I did here. Combined weight is at a distance of 30 cm away from the pivot. And when you solve for this equation, you notice that you get this equation. Wx, the weight of x times 0.7 meters is equals to Wy times 0.6 meters. This already tell you that Wx must be a smaller value. Okay, so Wx cannot be the heaviest object. Alright, so Wx must be a smaller value so that when it's multiplied by a bigger number, it can still equate Wy times 0.6 mathematically. Also, the same equation here also proves why option C is wrong. So option C tells you that the mass of X is the total mass of Y and Z. Basically, these two add together, you get the mass of X, which is not correct. Because when you solve for this, I just rearrange the equation. I just combine the 0.7 and 0.6 mathematically. You get this fraction over here, 6 over 7. And this tells you that the weight of X is 6 over 7 that of weight of Y. Okay, so when you add up these two, it will not give you add up the mass of Y and Z. It will not give you the mass of X at all. So option C is wrong. And finally, option D. If you look at the quantities in yellow, you will notice what is wrong with option D. When the long bar is balanced, the anti-clockwise moment of X, which is on the left hand side, is not equal to the sum of the turning moments of Y and Z. If I convert this phrase sum of turning moments of Y and Z, I will get this thing on the right over here. The sum of turning moment of Y and Z add together. So these two things over here are not the same. That's why D, the description for D is a bit wrong. Okay, and that's how you can solve for this question.